Good evening, everyone. Welcome to our event for tonight, friends. I'm Dr. Cameron Hummels. I'm a researcher at Caltech in astronomy and astrophysics, and this is our Los Angeles Astronomy on Tap for the first event of 2021. Welcome. We've got a super cool event tonight consisting of talks from two researchers prominent researchers in the field. Do you guys want to come on? Rachel and Igor. Rachel is a professor at University of Pittsburgh. Dr. Rachel Bezanson, and Dr. Igor Andreoni is a postdoctoral researcher here at Caltech. So for our audience, these events, we have these Astronomy on Tap events once a month. Our next one, heck, I don't remember off the top of my head. We also have a public lecture series, which is kind of a sister series to this. Our next lecture will be a week from this Friday at 7 p.m. Pacific time. And I don't know who's speaking yet, but I will soon, and I will announce it over the social media and through YouTube and such. So stay tuned to all of that. If this is your first time for the event, after I finish yapping incoherently, I will introduce, Rachel will be our first speaker. I'll introduce her. She'll speak for roughly 15 minutes about galactic cannibalism, which is going to be super cool. And then we will have a Q&A where you guys can ask questions in the comments, and we'll address that for a bit. And then I'll introduce Igor Andreoni, who will give a talk about the cosmic gold rush, which should be super cool. And that again will last about 15 minutes. Then with about 10 minutes of Q&A, 15 minutes of Q&A. And then we will do pub trivia with a interactive pub trivia that you guys can go to a website and answer there, and it'll pop up and populate our slides, and we'll be able to see what you guys are answering and see if you guys are all super geniuses, or see if you're not, or see if you're cheating by Googling the answers, which I have a feeling is what a lot of people are doing. But that's okay. That's okay. There are no prizes. There's no shame. Yeah.
There are worse things that could happen.
There are worse things. There are worse things that have happened this week. So, and last week. So, what beverages are you guys drinking right now?
I have a delicious stout in my Arecibo Observatory RIP mug. No, not mug, Stein.
Stein. That's cool. Where did you get it, at Arecibo?
I did indeed.
Excellent. Amazing.
I went in graduate school. It was awesome. I pretended like I was Jodie Foster, like too much.
That's awesome. Igor, do you also have an Arecibo Stein that you're consuming beverages from? I think you're.
Oh, you're muted.
Yeah, I was muted, and I was saying that you guys are way too cool for me, but I'll go for very simple blonde beer from Mexico. I might go for quantity more than quality, but it's really great stuff.
Yeah, it's very refreshing. I am drinking, again, kind of repping the brand, maybe not the Astronomy brand, but Fundamental Observation. This is a fine imperial stout from Bottle Logic that I'm super excited about. Yeah, so it's very, very tasty. Anyway.
Just realized this is going to be like a collector's item.
Oh yeah, it already
I could
is.
sell this on the black market. I'm not going to.
Yeah. So for our viewers, some of whom may be professional astronomers, right now the American Astronomical Society is having its semi-annual meeting virtually, because no one's going anywhere. And normally this is a week. It started today. It lasts, I think, I imagine this is a virtual meeting just like the normal meetings, which last about 4 days.
Yeah.
So this event lasts most of the week, and it means you'll see a lot of headlines this week, because a lot of press releases for new news stories regarding new results are embargoed until this meeting. And did you guys see any new results that were posted today or got picked up by press releases?
I'm not
think
sure
that's
that
on
I would
Neutron
have.
Stars.
There were a couple of other headlines that were distracting me.
There were.
Um,
Well, I saw one result. I wasn't really like you. I was distracted by things, but there was one result. Nanograv has an interesting result. So people in the audience may be familiar with the gravitational wave discovery from a few years ago by the LIGO team that was able to discern when two stellar mass black holes merged together, release gravitational waves, and we were able to pick up the warping of space-time here on Earth. There's another project called Nanograv, which uses pulsar timing array. So it's looking at pulsars. Pulsars are, you don't have to understand the physics of what pulsars are, but they're rotating neutron stars. But essentially, because they're called pulsars because they're pulsing at a regular frequency.
well, they're lighthousing.
Yeah, they're
at a regular frequency.
Exactly. So but from our perspective, we see these pulses of light occurring on a really, really, really regular interval. And when gravitational waves pass through that line of sight from the distant objects, sending its lighthouse pulses towards us, it'll get warped and it'll change the regularity of that signal. But it's very, very slight. And so if you have enough of these different pulsars around the sky that are all sending their pulses towards us, you can tease out if a gravitational wave went through multiple lines of sight and altered the timing from them, and figure out that there was some other gravitational wave event that caused that disturbance in the multiple lines of sight. And so people have been doing this. It's a project, it's an acronym called Nanograv, North American Gravitational other letters. I don't remember.
Wait, I can Google it.
Oh, yeah. But they've found a signal that's suggestive of a gravitational wave event from, they're more sensitive to larger mass black holes than LIGO. LIGO's mostly stellar mass black holes, but Nanograv is more sensitive to, I think, supermassive black holes, if I believe, much more massive, like millions of solar mass black holes. So yeah. They don't have like a Nobel winning result yet, or at least one that they're willing to put out into the media. But they have a very suggestive result. At least that's what I saw today in the news. So that's pretty exciting. But stay tuned this week. Hopefully there will be astronomy news that eclipses the other news that's in the media that's so problematic these days.
We're here to escape. I don't know about you. We're here to
astronomy escape.
Cheers to that.
Oh, that was really good. This is so good. Oh my gosh. Okay. Let's get started. So Dr. Rachel Bezanson is our first speaker. She is an assistant professor in the Department of Physics and Astronomy at the University of Pittsburgh. She is an observational astronomer whose research focuses on understanding the birth, lives, and deaths of galaxies through cosmic time. And she uses a wide range of telescopes on Earth and in space to identify and study galaxies in the very nearby and very distant universe and connect the evolutionary dots between those. In her spare time, you'll find her cooking or baking, doing yoga, walking her dog, or bicycling both inside and outside. And I should note, Rachel and I overlapped when we were both postdocs at the University of Arizona. Rachel was pretty much the most prestigious postdoc title is the Hubble postdoctoral fellowship, which she had for 3 years when she was at Arizona. And now she is an up and coming star at the University of Pittsburgh. So I'm very pleased.
I'm a galaxy. And also my most impressive experience or project at Arizona was the Tour de Bière.
The Tour de Bière. Yes, that's right. A bicycle tour around Tucson to the various craft breweries there. In a safe
Tying it back to this. Very safe, very responsible, lots of water.
Over 12 hours.
Astronomers.
12 hours of breweries and bicycling on isolated bicycle paths, not on roads shared
Do,
with.
do we have anything like that in Pasadena, Cameron?
No, there are too many cars in Pasadena. Too
Uh,
many cars
but there are breweries.
and not enough breweries is the bigger
We should do
problem.
something about that.
But
Got to
yeah,
come to Pittsburgh. We got lots of hills, lots of cars, and lots of breweries.
okay.
It would be a much harder bike ride.
That would be a challenge.
Sounds
yes.
awesome.
Okay, sorry.
Okay. I will, Igor and I will disappear and we'll let you take it away, Rachel.
Awesome. Okay. Let's prove that I know how to use technology. You'd think by now. Okay. You should see my screen, but it's lagging on the YouTube, so I can't.
No, it
tell
looks
that.
great.
Okay. Awesome.
Cannibalism.
Yeah. So I'm really happy to be giving this talk here at AOT in LA. I would much rather be in LA, in a brewery, in a bar, drinking beer with all of you, but you're gonna have to settle for my third floor, you know, gym, teaching space, whatever else this room is. Today I'm gonna tell you, or tonight for me, I'm gonna tell you a little bit about how you build a really big galaxy, the biggest galaxies. And I'm starting with a punchline. The punchline is cannibalism, galaxies eating galaxies. Here it's actually galaxies drinking galaxies, but you'll, you know, I don't know, forgive my punny start. So I thought everybody, whoever's calling into this, could probably use an escape. So I figured we could zoom out, and here is a zoomed out picture, unclouded by any of the news that's been kind of floating around. And we are all here in this little dot. Actually, I'm not sure if you can see my cursor, but we'll find out. We live here. This is a kind of zoomed out cartoon of the Milky Way for perhaps obvious, perhaps not obvious reasons. We can't take a picture of the Milky Way because we can't yet get outside of the Milky Way. And just for a sense of scale, you would have to travel 75,000 years just to get from where we are here to this far edge of the Milky Way. The Milky Way is a galaxy. It's our galaxy. Galaxies in general are huge collections of stuff. Any stuff that you can think of, it's probably in a galaxy. Galaxies are full of stars and gas and black holes and planets and people and beer and dark matter. All of that kind of is collected in the Milky Way. It's collected into this kind of disc-like object that rotates around and has spiral arms, and it's nice and it's beautiful. And just to kind of give you a further sense of scale, the Milky Way is extremely large. It's also extremely massive. So it has a mass that's something like 50 billion times the mass of the sun. If you don't have, feel free to ask questions and Cameron will filter them to me when he sees fit. So if you don't have an intuition for how massive the sun is, I'm not sure I'm going to really help you, but let me try. So the sun is itself 300,000 times more massive than the Earth. And the Earth is about 10 trillion times as massive as the total mass of all of the humans that live on the Earth. Or it's as massive as 2 with 41 zeros pints of beer. And that's just the mass in the normal stuff, in the stars. So it's 20 times more massive if you include dark matter. In short, galaxies are very large. The Milky Way is very large. There are smaller galaxies also, but I actually want to focus on even bigger galaxies. Here's a picture of a bigger galaxy, meet M87. M87 is significantly more massive than the Milky Way. And the type of folks who log into this kind of event may have also seen M87 in the news, but they may have seen a very different view of this galaxy, actually something at the very heart of the galaxy. So this is the XKCD version of the Event Horizon Telescope image of the supermassive black hole at the very center of M87. So the image of the hot gas that's accreting around that very massive black hole. I'm not going to talk about it anymore, but I figured I'd mention this. So this is M87. I mean, M87 looks extremely different from the galaxy that we live in. And so I'm going to talk just really briefly about how you would make a galaxy that looks like this. So things that we know. First of all, I could tell you, and you can take my word for it, or I can, point you to the literature. We know that the stars in this galaxy are old. And part of that we know because of the colors of those stars. The stars are, over 10 billion years old. That's old, even for a galaxy. The other thing we know is that for the most part, this is a pretty boring looking galaxy. I have to say, as somebody who studies massive galaxies, I'm used to this. I think it's beautiful, but it's kind of boring looking compared to the Milky Way. So if you'll bear with me, by boring, I mean it's smooth. It definitely doesn't look like the Milky Way, and it definitely doesn't look like any galaxy that's actively making stars. And so for a long time, we just assumed that big, massive galaxies like this were relics of a much earlier time in cosmic history. Okay, so bear with this. There were kind of two previous models up until about the last 15 years or so. There were two models to make a galaxy that looks like this. And the first of those models, I'm going to call this the Lady Gaga model, but actually the technical term is monolithic collapse, says that actually those galaxies form in this kind of three-dimensionally round and smooth shape because they formed so violently. They didn't have time to form the nice regularly rotating disk galaxy structures with the spiral arms that we see. So in this model, all of the stars form kind of all at once in this enormous burst. It's extremely violent, and then the stars just kind of get old and old and old until we see them today. The other model to produce a massive galaxy like this, we'll call this the Amy Schumer of galaxy formation models, says that these galaxies were formed by taking two big Milky Way-like galaxies and smashing them together. And what that accomplishes is, you destroy that nice orderly pattern, those nice orderly rotations. Most incarnations of this model also truncate the star formation at the same time. And so you're left with a galaxy that has a different shape, and it's no longer forming stars. So it just kind of sits there and passively ages. And the starting parts of these two models, the Lady Gaga or the Amy Schumer models, they look very different. But that passive aging was this kind of assumption of most studies. The thing that changed is that we started to be able to look into the more and more distant universe, and specifically, most of this work was done with the Hubble Space Telescope. Okay, so let me take a step back. Galaxies take this process takes billions of years. In any case, the stars themselves are something like 10 billion years old. So I'm not waiting to watch this process happening in any one galaxy. And instead, what we do is we look at the population of galaxies, or I look at the population of galaxies further and further into the distance. And because the speed of light is finite, That means that as I look further and further in the distance, I'm looking further and further in the past. And so the Hubble Space Telescope and other telescopes on the ground, and soon the James Webb Space Telescope, which I could talk about forever, but I'm not going to, are able to collect light from the very, very distant past. And in the last 15 or so years, we've been able to look 10 billion years in the past and actually see what the progenitors, the galaxies that will turn into galaxies like M87, looked like. So those models that I showed you, both of the models make a prediction. So the hypothesis is if the stars are greater than 10 billion years old, both Lady Gaga and Amy Schumer models would make a prediction that those galaxies, if we found them in the distant universe, would look pretty similar. And I can be a little bit more careful. The colors of the galaxies would be different because the stars would be younger. But that dramatic event still wouldn't have happened yet, or had already happened. Sorry, let me get my chronology straight. And what we found was very much not that case. So when we looked at all of the galaxies that could turn into an M87-like galaxy today, they were much more compact. They were smaller in physical extent by a factor of 3 to 5, depending on how you make the comparison. And therefore, the density goes as that cubed. So they were extraordinarily dense objects. Here's an image. These are kind of extreme examples. These are on the left. This is my favorite massive galaxy in the nearby universe, NGC 5846. Not for any good reason, just because I stared at it for 8 nights by myself at the top of a mountain in at a telescope. Is in my 3rd year of graduate school, so I'm just used to staring at this galaxy. Kind of boring thing to stare at, but I liked it. On the same physical scale, here's a galaxy 10 billion years ago, but I have put it at the same physical scale, and they have approximately the same mass. So in the early universe, these galaxies were extraordinarily structurally different, and we expected them to be really the same. So we were left with this conundrum. Neither of our models worked, and I'm going to skip pretty quickly to the punchline, which is that those very, very dense galaxies that we saw in the very distant universe actually appear to reside within the centers of the M87-like galaxies today. So the densities are very similar. And the picture that we have in our head is that central core forms first, and then the outer envelope builds up over time. So you should imagine, here's a picture of a Tootsie Pop. Don't imagine the way that you would eat a Tootsie Pop, but instead the way that you would make a Tootsie Pop. And the physical process that we think drives this is, you guessed it, because I told you, oops, cannibalism. Sorry, nobody has ever said cannibalism in that kind of enthusiastic tone before. But the thing that was missing from those models was that galaxies don't live in isolation. Instead, they keep bringing in their little buddies to the party. It's not one crazy train wreck event. It's not 2 Milky Ways that smash together most of the time, although that does occasionally happen. But rather, you can see in this simulation, that is an oversimplified simulation, but we think is a pretty representative simulation of what at least the gravitational effects would be, is that you see that this big galaxy is formed by kind of pulling in and pulling off the stars from its neighbor. And maybe cannibalism is the wrong word, but it kind of acts like the Borg and brings everything into its body. And you end up with something that is much more boring than a Milky Way. Okay, so I just wanted to say, or to emphasize, that even though we zoomed out, and even though I'm talking about a galaxy that we'll probably never go to, you shouldn't feel left out. And if you're patient, more patient than you probably can be, this fate can also be yours. So this is kind of one of my favorite press release movies of all times. It came out something like 8 years ago. And it came from a analysis that basically measured the relative positions of the Milky Way and its big neighbor, the Andromeda Galaxy. But you can see there's time in the lower left-hand corner of this video. And the Milky Way doesn't live in isolation. And eventually, if you can wait long enough, billions of years, then actually the Milky Way will go through model number 2, and perhaps end up looking something very much like M87. You can see that in this simulation. And then it just kind of tones down. This is my favorite part. My favorite part about this was that in addition, so this is when you go to a dark space from the surface of the Earth, you can see the plane of the Milky Way. But if you lived in a very massive galaxy, we call them elliptical galaxies, these round, boring monsters, then the distribution of stars in the sky would be very different. And indeed, this is what it looks like today. And if I can get this to play, they simulated what this would start to look like as Andromeda starts to come in closer, as the two galaxies start to interact, as their stars get ripped up around us. And now we live inside of a smooth monster galaxy. And now 7 billion years in the future, so I wouldn't get too worried about this. I think there are more imminent threats. Furthermore, the stars are spread out pretty significantly. So probably the Earth would come out unscathed if we haven't destroyed it yet on our own. So that's the end of my talk. I can see that there were a bunch of comments and perhaps some questions in there. I'll wrap it up, and Cameron, you can take over.
Excellent presentation. Thank you, Rachel. That was great. I haven't seen this final video. I've only seen snaps from the final video, but I love it.
I kind of love this. I'm kind of obsessed.
Yeah, it's super good. Yeah, we have lots of questions from our audience. Let's see. One of the first ones is, are globular clusters the remains of galaxy mergers?
So,
well, I guess first we should make sure the audience knows what a globular cluster is.
Yeah, that's fair. So globular clusters are extraordinarily dense collections of stars. They live generally in the halo of the Milky Way, so they don't live in the nice organized plane, but they actually live in a distribution that actually follows a distribution similar to the stars in an elliptical galaxy. But they're very dense, and the difference between a globular cluster and a galaxy really is the dark matter. Globular clusters aren't generally thought to have dark matter, and so we think they form through a slightly different channel than galaxies do, and so they're not just small galaxies that have been stripped of their outskirts. But actually, the formation of globular clusters is probably something more like the Lady Gaga formation channel. So they probably form in some kind of really extreme burst of star formation. But it is my understanding that this is still an open area of research, and maybe not like the sexiest, but I study big boring galaxies. So what am I?
No, I mean, I think it's still open, and I think it is still really interesting. There was a KITP session on it a year ago
Yeah.
about the formation of globulars, and I think it's pretty exciting. But yeah,
They're super cool, and they're really like powerful tests of different formation models for the Milky Way too. Yeah.
and observers, people who have telescopes, may have seen. You can easily see globular clusters. In fact, there's at least one naked eye globular cluster. That Hercules cluster, M13, is usually bright enough that you can see it naked eye, I believe. Oh, well,
Certainly binoculars.
in really, really dark skies, you should be able to see it. But yeah, it's as the name suggests. It looks like a big glob because it's a big, dense cotton ball of stars.
Yeah.
Okay, lots of other questions. Do we have HR diagrams? Okay, this is already an advanced question. Do you have HR diagrams of these galaxies, or do we estimate the age some other way?
Yeah, so no, we generally don't have HR diagrams for most external galaxies. So HR diagrams are specific plots that astronomers use to study individual stars and the distribution of individual stars that tells you about the different generations of star formation that have occurred in that region of the sky. The technique is similar, it's just all integrated. So if you're familiar enough to ask me about an HR diagram, you basically just collapse the distribution in magnitude and just look at flux as a function of color, approximately. But it's a little more complicated than that, but honestly, it's not that much more complicated than that.
Here's a question. You're referring to things like distance and time and past, but past in relation to what present? Are we calling our center the present? And this person is trying to suggest they're really asking this as a serious question. They're not just trying to be a problematic person, because yeah.
No, I think that's a very fair question. Yeah. So, defining your reference frame is the most important thing to do when you're studying things in an evolving universe. So indeed, our time zero is now, as the time of observation. And so let's see. And the difference between, when I observed something last week and when I observed something 3 years ago for galaxies doesn't matter. There are some objects, some astronomical observations, you might hear about them next, where time, human perceived time matters. But in the context of galaxies, yeah, our time is zero, and it's zero whether you're talking about when you were born or when you went to the telescope.
How do mergers quench star formation? Does it have to do with disrupting the gas inflow?
So that's a great question. It's a question that we argue about. So the short answer is many people think that they have, well, there are many suggestions. So star formation basically requires that you have cold gas. And so the shortest answer is that the way that you can shut off star formation is you can either get rid of the gas or you can heat up the gas and keep it from cooling down.
Just so our viewers know, why do we need the cold gas? What does the cold gas do?
Oh, the cold gas is the thing that collapses and gravitationally collapses and turns into a star.
Okay.
Right. So there are lots of ways that people have suggested to heat up, expel the gas in galaxies. Some of that happens just naturally by stirring things up, you heat things up. So when you have a dramatic merger, that'll heat things up. But mostly gas will cool down again. And so that doesn't usually work. Some people will point to, the the image of the M87 that I chose it suggestively for a reason. M87 has this gigantic supermassive black hole. And yes, that is actually, I think, a grammatically correct thing to say, because supermassive black hole is the title, is the noun. But anyway, it has this huge supermassive black hole. It does seem redundant. But anyways, and it is spewing out this jet of highly energetic plasma. And so the thought is that can help to heat up or maintain the temperature of the gas and keep it from cooling. Some people think that can blow out the gas. Some people think that the dark matter halo actually plays a role. Anyway, I could go on and give an entire colloquium length talk about this, but suffice to say, this is a thing we argue about.
Indeed. All right. We'll ask a couple more questions and then move on to Igor. When two spiral large galaxies, like that video that you showed, when two spiral large galaxies merge, is there any way that a bigger spiral is the result? Or is it basically just game over for the structure and you always end up with that kind of Milkomeda elliptical mass of stars?
I feel like there's a name for Milkomeda, but I like Milkomeda. The short answer is absolutely. You can reform a gigantic monster disk. And it depends. So basically it's a question of angular momentum, right? So as you have two galaxies, imagine you have two galaxies that come in like this. Well, there are orbits that would allow those the initial rotations to just kind of add together. The other option is that you can reform a disk. So basically, the reason that galaxies form as disks anyways is because when you have a collapsing cloud of gas, there will be some net angular momentum that spins up like a ice skater. When they pull their arms in, they spin up faster. That basically happens to the gas. And it preferentially happens along one axis. So it pancakes in one direction, just collapses due to gravity. But angular momentum supports against that collapse in one dimension. So you can reform a disk. Even if you were to throw a whole bunch of gas, a lot of gas at M87, you could probably reform. It would have to be a lot of gas. Maybe I should use a smaller galaxy than M87. But yeah. So the short answer is yes, absolutely. You could end up with a disk. It depends on the orbits and it depends on the amount of gas.
Exactly. Yeah, that's great. And simulations bear that out as well. If you have two disk galaxies that come in along their plane and there's all like the same angular momentum contact, they're all rotating in the same, my janky rotational demonstration. But if they all have the angular momentum coming together, you'll form an output. Yeah. Whereas if they're rotating, they'll
and this is a super important question because actually, like, I don't talk about this at all, but like one of the things that we're starting to learn is that those tiny little progenitors of M87 like galaxies, they actually don't look like little M87s. They actually still, even though they don't have ongoing star formation, they look like little disks. So you can see them rotating. So, they rotate really significantly. And how we form them, I don't know. It's still an open question.
Last question is, how long is it going to take for the LMC, the Large Magellanic Cloud and the Small Magellanic Clouds to merge with our own Milky Way galaxy? So for viewers who are in the Northern Hemisphere, you may not be familiar. There's the LMC and the SMC, the Large Magellanic Cloud and the Small Magellanic Cloud, which are these small satellite galaxies that are orbiting around the Milky Way. And they're slowly, presumably, going to funnel in, and we're going to eat them as the cannibals do.
Can I phone a friend? Gertina would be able to answer this immediately. It's billions of years. It's of order billions of years. But we actually have a friend who literally studies the orbits of
like the world expert on the orbit of the LMC and the SMC. She's a professor. Her name's Gertina Vesla. and she's a professor at University of Arizona and super good. And in fact, she was involved in the study that generated that video
of the Milky Way
of the Milky Way and Andromeda merging. Yeah, she's a badass lady. So
anyway, so like I could text Gertina and she would have the specific answer, but but it's billions of years. It's, you know, it's a shorter time scale, I think, than Milkdromeda, but I think comparable, actually. But the LMC and the SMC, I think, will merge sooner than that.
yes, they will merge with each other, and then that whole system will merge with us. So it's a hierarchical kind of thing.
It would look a lot like that simulation of the massive galaxy. Indeed. Right? Yeah. Okay.
We're gonna have to move on because we still have Igor to speak, and we still have pub trivia, which is gonna be super fun. So if you have additional questions, I don't know what to say. Ask them in the comments, and we'll try and address them in the comments while the rest is going on. But
yeah, I can do that. But
okay.
Don't stop asking questions, because there's another awesome talk.
Yeah, that's right. Igor, are you there? Ah, there he is. Excellent.
I'm back.
Excellent, excellent. Okay, so Dr. Igor Andreoni is a postdoctoral fellow in observational astronomy here at Caltech. He uses large telescopes to discover new sources that appear in the night sky. And those sources, the sources that he prefers, are the fastest ones, which are the most challenging to find, but they hide potentially very interesting secrets. As you may expect from his Italian background, Igor loves soccer, he loves coffee, and he loves fishing from the ocean shore. So yeah, Igor and I have overlapped now you've been in the department for 3 years? Is that right?
Yeah, this is my third year.
Third year, yeah.
Right.
Yeah, he's very involved in something called growth, which is similar to maybe some of the stuff that he's going to talk about, which is looking for these kind of short-lived transient events that are occurring in the sky. So it should be super exciting. Do you want to take over?
Yes, I will.
Excellent.
And one more shout out to Rachel's talk. That was really awesome.
It was great.
All right. Can you see my screen?
Yeah, it looks good.
Fine. All right. Let's start then. So, well, hi everyone. And I would like to talk tonight about a bit where to find gold in the universe, and maybe actually how we can chase after it and find more. Who knows? But before getting too far away from the Earth, I would like us to get on the same page about something, which is that the universe is a very, very rich and diverse place. So diversity is really what makes the beauty, if you want, in the world we live. And in particular, you can see here the periodic table of elements. Don't have to look too closely to it. Chemistry may not be your thing, like it's not my thing. But here are summarized a bit all the elements that we know about. And they include, for example, carbon, just up here, which is the basic brick for life as we know it. And if you look more in the middle of the periodic table, you find platinum and you find gold. So the first part of this little chat will be about how can we actually get there in the periodic table to form platinum, gold, and such precious elements. And how can we get there if we know that at the very beginning of time, at the time of Big Bang, we had only hydrogen and helium. So with all due respect for my cosmologist friends, the universe back then can be considered a bit boring. There's just not too much material to play with. But fortunately, there is energy on top of these elements. There is gravity that pulls them together and puts them so close that they can ignite and stars can form. Now, how can we get from these two elements to the full periodic table? Some elements are formed within stars, very close to the nucleus, in the core, right? For example, carbon that we talked about a second ago is synthesized in the nuclei of stars. And now you can wonder, if all these elements are created in stars, how can we free them? The answer is pretty easy. We just blow a star up. Not really we do it. Gravity again does the job. Just keeps pulling until all the fuel for nuclear reactions just run out. And then the core collapses and this gigantic supernova explosion happens. And they liberate a lot of mass, a lot of ejecta, a lot of new elements in the universe that then they go and reach galaxies and form new and richer stars. So if we consider also this type of explosions, along with a couple of other physical processes, we start getting a more a periodic table that looks more like what we know. We can see that we have more elements, but we're still very far away from where we want to get, and surely don't see much gold over there. In order to fill out the periodic table, one really needs to look into, well, maybe dying low mass stars, but the process that I like the most are the merging of neutron stars, that many of us believe that they are the dominant site where these very heavy elements are created. And these mergers are truly dramatic events. So neutron stars are special stars, are the remnant that is left over after these great massive supernova explosions. And they're super dense. They are not very big in size, maybe, yeah, pretty much the size of Pasadena if you want. However, they include a mass pretty much equal to the mass of the sun. So you can imagine what can happen when you have two of those crashing against each other. It must be quite a spectacular thing. But on top of what could happen if you are witnessing this merger from nearby, now we know, and thanks to Einstein's theory, we actually that was predicted, that gravitational waves are released when two neutron stars keep spiraling closer and closer to each other, and then a huge burst of these gravitational waves is released when they finally merge. And scientists have been just incredible and resilient enough to build instruments based on laser interferometry, two of which actually are here in the US. They're called the Ligo Instruments. And with Ligo and then Virgo and Kagra, you can detect these gravitational waves, which are nothing other than space-time that gets stretched and pulled and squished by these perturbations, this ripple in the space-time that propagate at the speed of light and then dissipate throughout the universe. So we can probably go more into general relativity theory to understand what we're talking about. But I see down there President Obama, who's giving me the okay to keep going with the talk, and just trust me on this one. Gravitational waves do exist, and LIGO and Virgo have proven to be able to detect them. The problem is that we don't really know when the interferometers are going to detect them. Definitely when they are online, and later I will mention when we can expect the instrument to be just turned on. But in the 1-2 years maybe that they stay on, they keep collecting data, we can receive this signal from binary neutron star mergers really at any time. And that's quite a highlight, quite an important thing to keep in mind if you do a job like mine. Me and other friends were like a bit like doctors, like the actually useful medical doctors who have to be on the call if something could happen. Sorry, in their case, if something that needs their help happens. In our case, if something very cool happens. And this happened at least once in a truly spectacular way on August 17, 2017, in a galaxy that is far away, about 130 million light years away, but still in what we consider the nearby universe. And these two neutron stars spiral closer and closer to each other and finally merged in this truly amazing explosion that not only gave birth to a jet of material and radiation that we could detect as a GRB, a gamma ray burst, but also it ejected a lot of mass in a pretty much isotropic way. That's the sort of cloud that you could see coming from the center of the explosion in the video that has just played. And these ejecta are the key for us to find gold. In particular, that's where we expect to find a very bright, very bright transient emission called kilonova that we can observe in the optical and the infrared. So with our telescopes, why not? And of course, this is so bright that we can see such event from far away, from further than from within the Milky Way. And what does a transient look like? In particular, what did the kilonova associated to this gravitational wave event GW170817 look like? So in this image here, you can see a galaxy. It kind of looks like a star because it looks pretty regular, pretty circular, but it is a galaxy, it's the host of the transient. And now you will see appearing the transient, a new source. That's exactly what we are looking for, what we want to get on sky with our telescope to find. And now I will play a little video in which you will see time passing. And then you will see how rapidly this source evolves in its color and its luminosity. And all these data were acquired with the SkyMapper telescope, which is located in Australia, a country that I truly love, where I did my PhD. And it was really good fun to work together with local astronomers to work on this event. And you can see that in less than a week, here we're talking about August 24th, we started August 17. In about a week, the source has already disappeared. It's already become too faint for us to observe with telescopes that are not gigantic or are not working at other wavelengths. And if you like to talk wavelengths and you know a little bit about spectroscopy, which is light that is no more accumulated in a CCD as an image, but is dispersed so that we can see the luminosity as a function of wavelength, we can have an even better sense of the color and the color evolution of this transient. Maybe some of you who paid particularly good attention to the previous video, you could see that the dot, the new source that appeared, was very blue to start with, and then it evolved. It became redder and redder. And this was also observed in spectral observations, not just the images. So we could see that the luminosity keeps decreasing with time. Again, here at the top right, you can see the days that are passing from the time of the explosion. And you can see two things. It becomes fainter. The signal becomes redder, so more luminous toward the right side rather than the left side. And there are some weird wiggling shapes that come up that we couldn't quite see at the beginning, where the shape of the spectrum was more regular. What is this? We're actually looking directly at the ejecta that are so full of radioactive elements that keep decaying. And so many transitions are happening because a significant fraction of them has very high atomic number. They are the heavy elements that we were looking for. That's where we expect to find gold. And something quite amazing is then comparing the data that we got with the predictions, with what theorists have thought could happen. And they ran some simulations, maybe with computers. And like in this plot here, you can see the theory, which is indicated with the red line, compared to the data which is the black line. Now, some of you may say that the match is not perfect, but trust me, this is an amazing match. And this allows us to tell, for example, how much mass was there in the eject of the explosion, its velocity. And we can even tell what fraction of heavy elements we can expect to be there in the ejecta. And why did I choose to call all this topic, I want to talk about a gold rush, because literally half of the astronomical community in the world just dropped everything they were doing when GW 17870 happened and started observing this new transient. And as Cameron and Rachel said before, in this case, unlike galaxies, time is of the essence. We really want to get as much data as possible, as fast as possible. The source just disappears too quickly. And in this video, you can see as the markers just pop a bit bigger, that's when observations happened at a certain observatory site. And if you look at the timestamp, again, here we're talking a time frame of about 2 weeks to 3 weeks from the merger. So this was, in fact, a gold rush. All the astronomers, pretty much all the astronomers in the world, just disregarding for a little bit what they were doing in order to find gold that can be found in the ejecta of this merger. And now, this hopefully was not the only gold rush that we can participate. A little bit of the timeline also for you to keep yourself up to date with what's going on in the field. Once again, things get particularly interesting, also not just for the discovery aspect, but also to do more science with what's called multi-messenger astronomy, when the gravitational wave observatories are online. So the first run, O1, was in 2015-16. And the sensitivity back then was not that good. But in O2, in 2016 and 17, there was the discovery of the GW 17817. And it's quite remarkable, if you think about it, that just observing that one event, we could have estimated that about 100 Earth masses of gold was produced just in that site because of that merger. And even more, about 5 times more, 500 Earth masses worth of platinum. That's really something that would justify another gold rush. And then in 2019, 2020, we had O3, where people were more ready, more instruments were there, really just ready to face this challenge of finding these transits, which are a bit like hidden needles in haystacks. They're very hard to find. And unfortunately, we didn't find gold this time. We searched very hard, but we didn't find what we call an electromagnetic counterpart to any gravitational wave event. And we're surely looking forward to O4, which hopefully will start in 2022. What do we need in order to be successful in the gold rush? So that's the final part of what I want to talk to you about. What do we need to be ready, to have our gear ready? First of all, we need friends. We need collaborators, if you want, colleagues. We want them, again, go diversity. We want them to be in different parts of the world, in different nations, in the northern and the southern hemisphere. We really want the party to never stop, because if something interesting happens, we really want to be able to monitoring for as long as possible. We can't just wait for it to be night at my favorite observatory. I need some of my friends to observe with their telescope, maybe with different instruments from different locations. And that's one of the primary reasons why our growth collaboration exists in the first place. Second, we need telescopes. Within the collaboration, we count at least 10 telescopes, quite a few. Here, I'm just showing a couple that that are particularly close to my heart, that I've used quite extensively, especially in the past few years. One is called DECAM, or the Dark Energy Camera, which is located in Chile. And one is ZTF, the Zwicky Transient Facility, which was built at Caltech and operates here in California at Palomar Observatory. Here, just to give you an idea of the resolution that we can get with DECAM. You see that smudge here on the top right of this CCD. It's probably maybe a satellite galaxy to this bigger one that you see on the bottom left. And during my PhD, I did find a transient source in this little galaxy. But things get quite impressive, I think, if you realize how little portion of the big field of view of DECAM this image is. So this is quite a challenge to find new transients in so much data, but it's really exciting. And that's what we need to find the needle in the haystack. How can you contribute to it if you want in the future, if you want to be more involved with the search? One example is via the Zooniverse, which is a website that allows you to really interact with professional observers, to tell your opinion and to help them in the search. And for example, during 03, so last year, I was very, very privileged to be one of the principal investigators of the follow-up of gravitational waves with DECAM. And we managed to convince the director to make the data public immediately. This is not something standard because the camera itself costed more than $100 million. These data are very precious, so it was, I think, really great that we could make them available to people straight away, and someone in the community was downloading the data and pulling up galaxies and looking for new sources that we didn't know about before. And to conclude, I would like to share a web page that you might find interesting, because we said that to be successful, you need friends, you need telescopes, but also you need a map to find the treasure, right? There is this service that some other astronomers created called the Treasure Map that collects all these gravitational wave events as they come in. And the idea here is to present a map for each of them that tells you, based on the information that is released by the LIGO and Virgo collaboration, where we are more likely to find this counterpart, this kilonova, in the sky, and where we're less likely to find it. This is a particularly challenging sky map that we received that correspond to the gravitational wave event GW 190425. And you can see that there is a huge part of sky where we can expect to find something interesting. And quite funnily, if you click on Swift Bat on the right, you can see where this gamma ray telescope was observing at the time of the merger. And you can see that we were in the wrong side of the world, which is bad, which is a problem. It makes our job more difficult. So how can we effectively search for these counterparts? There are two strategies that we would like to leave you with. One is called galaxy targeting strategy. Basically, people pull out a list of galaxies that we think they are at the right distance, that we expect from the information from gravitational waves, and that they are within this sky map. And instruments such as the MMT or the Swift XRT and UVOT, that's what they did. They pulled up a list of galaxies. Now I will zoom in some of them, and you can see at the center of these squares or circles, the galaxy where people were trying to find new sources in. Hopefully that one would be the host, like it happened for GW 170817. So this is one way of looking for counterparts. The other way is called a synoptic search. So we ignore any galaxy catalog. We only consider the sky map. We only consider locations where we can observe them. And here now you should see with these purple squares, all the location where we observed from Caltech and from, in general, us in the growth collaboration with ZTF. And my friend Michael Coughlin, who I think is actually online today as well, wrote a fantastic paper presenting the data that we acquired here. But more work is needed in the future. We will need to be ready at any time of the night and of the day. And hopefully some of you will be able to join us in the future. And well, thanks so much for listening to me today.
Excellent. Thank you, Igor. Thank you for the wonderful talk. Yeah, I liked all of the gold rush references. I'm a big fan of those. So we had a lot of questions throughout the talk. I'll throw a few of them at you, and that is, if the neutron stars are so small, you said they were the size of Pasadena, how do they actually manage to hit each other in the huge void of outer space?
Yeah, that's really an amazing question. It's a very difficult question to answer because first of all, you need to have two of them that are pretty close. So this means that there are some systems that actually turn out to be quite a few. Almost half of the stars that we see in the sky are actually binary systems. They're made of two stars. But these are even more special because if they are neutron stars now, it means that they used to be very massive stars earlier on. So both of them had to undergo some evolution. They had to remain in a binary or become a binary, depending which model you prefer. And then one more question that is probably even more complicated to explain: how can they get closer and closer and closer in void? And the answer is gravitational waves. Gravitational waves, one way that we know they exist is because we see these binary systems getting closer and closer. Their period changes because energy is dissipated by gravitational wave radiation. This was one of the most glorious predictions of Einstein's theory of relativity.
Indeed. Someone asks, what is the state of matter in a neutron star, just in general, prior to these collisions?
Yeah, that's another question that we're actually trying to address thanks to these multi-messenger studies. It's quite a mystery. You really need to be a nuclear matter expert. Some say that there are superfluids or even quark matter at the center of these neutron stars. The shape and the ways that particles combine in their nuclei are really, really exotic. And that's why they constitute some of the best laboratories you can imagine, because we couldn't reproduce those conditions on Earth. So one of the challenging and at the same time, one of the goals of these multi-messenger studies is to learn more about the equation of state of neutron stars, which basically is the study of its density as a function of the radius, to say it in a simple way.
Indeed. Related to the discussion of the kilonova, someone wanted to see, is a kilonova really 1,000 times brighter, as kilo means 1,000? Is kilonova really 1,000 times brighter than nova? Or, why was that chosen as the verbiage?
Yeah, it's a question we're trying to address. The prediction were about 1,000 times earlier, then they became much fainter than that, then much larger than that. Then we found out it is indeed way larger than 1,000 times. But the distribution, we call it, of properties of kilonova and the kilonova luminosity function, which means basically, let's go count how many kilonovae are brighter than, say, 1,000 times a nova, how many brighter than 1,000,000 times a nova, and so on and so forth, is actually a topic we have just published a paper about. We managed, thanks to all the information we collected during 2003, thanks to the non-detections. So that's one nice aspect of science. Sometimes you're looking for something, you don't find it, but still you can learn something about the universe. That's what we tried to do. We tried to combine all the probability of non-detection that we have and try to answer, try to put better constraints on this kilonova luminosity function.
And a related question, what's the rate of the mergers like this in the Milky Way?
In the Milky Way.
Or in
Okay.
general, I suppose, but certainly the Milky Way, it's much easier to observe these sorts of things.
Yeah, they're definitely rare. You can think like, so a supernova is expected to happen in our galaxy every, say, 100 years. Probably a merger of this type is a very tiny fraction of the rate of supernovae, probably about 1 part in 100 or a part in 1,000. So basically, we could expect one of these merger every probably 10,000 years. But I can tell you a number on the spot in units of number of kilonovae per gigaparsec cube per year, which we know it's about few hundreds to maybe at most 2,000. And one can then rescale that rate back to the Milky Way.
What was it? Events per year per cubic megaparsec?
Gigaparsec.
Oh, jeez. Okay.
And I mean, you're really asking me to go from there to the Milky Way, with this. So, yeah. I mean, I give you estimates.
Very, very large. The size of the Milky Way, like gravitational volume, let's see, is like a megaparsec in diameter. No, not even a megaparsec in diameter. Like,
yeah, well, like more like 10
megaparsec is fine.
For halo, the size of the halo.
Fine.
So like 1 megaparsec, and you're talking about a cubic gigaparsec, which is 1 billion times the size of that. So, okay. Anyway, we're getting off topic. Okay. Thank you for the wonderful talk, Igor. That was wonderful. In interests of time, because I don't want to keep everybody up too late, including Rachel, who it's already Eastern time, so it's nearing midnight over there.
Cameron, I'm an observer. This is normal.
We will move on to our astronomy themed pub trivia, if everyone is ready. Rachel, your video's off, and you're muted. You're hidden. You're hidden from the world.
I didn't want to be like, interrupty. I don't know.
You can Zoom bomb us. You can Zoom bomb. Okay, so everybody, we have this pub trivia component to our Astronomy on Tap nights. Let me see if I can make this actually work. Okay. It uses a program, a website called Mentimeter, which is like Poll Everywhere. It's one of these newfangled websites. And all right, can you guys see that slide? Okay, so as it says, you need to go to this menti.com and enter a code in order to be able to participate in the pub trivia. We ask that you do not look this up in Google, the questions up in Google. We have no ability to police that. But anyway.
We don't have any prizes either.
No prizes. I'm not going to be sending trinkets to your houses during the pandemic. I'm sorry. I mean, we had pretty good prizes. We had like books by, I don't know, Bill Nye, by Carl Sagan. Cool books.
The before times.
The before times. All right, so everybody's there. I'll just move on to the questions, or maybe I'll move on to the questions. It's just gonna work. Okay, can you guys see the questions at least? Igor and Rachel? Yep. All right, so some new satellites are being developed from what substance in order to decrease space junk? Because we all know there's more and more satellites going into space. And we risk problems with the abundance of stuff in low Earth orbit. Yes, that is a good answer. That is a wonderful answer. I'm asking for what the substance is that these satellites. Carbon. Okay, that's fair. Wood. Interesting. All right. Yeah. So the idea is that
witches.
More and more things are going into space, and we risk the Kessler syndrome, where these things slam into each other and create more and more fragments that are all traveling at, you know, hyperspeeds and running into each other. And also when these things get decommissioned, they come into our atmosphere and they burn up. And if it's all made of silica or aluminum, it's just going to disperse and create huge clouds of vaporized metal in the atmosphere. So, wow, we've got all kinds of stuff. Wood like an IKEA sat. Yes. Neutronium. Neutronium. Okay. Yes, the answer, as many people have correctly guessed, is in fact wood. There's a Japanese company, coincidentally co-sponsored with a forestry company, which I guess that makes sense, that's looking into ways to create satellites made out of wood so that when they are decommissioned, they just burn up and don't create any kind of crazy like amounts of silica or aluminum in the atmosphere that eventually percolates down to us and causes us respiratory issues or whatnot. And yeah, it's interesting. It seems kind of retro to use wood in your satellites. And I guess you have to worry about the launch mechanism so it doesn't catch fire, but interesting nonetheless.
Seems awesome. Awesome is the word you're looking for, awesome. I think.
All right, so how about this? How fast do gravitational waves travel? Related to the stuff that Igor was talking about, we've got several different options. We've got instantaneous, speed of light, √2 of the speed of light, variable, and we don't even know. And the audience is not tricked by any of this. The audience knows what they're doing here. The audience says the speed of light. What do you guys say?
Us guys?
Oh yeah, you guys are the guys.
We like to say we don't know, so we get more fundings to do more research.
But we do know, and it's the speed of light.
We do. That was measured so well.
Yeah, that is one of the things we know very, very well.
Yeah, it's kind of, yes. So the answer correctly guessed by everyone is in fact the speed of light.
That's a super cool.
I know. I love that.
Yeah, some people still wonder if that could change if travels through like an extremely dense medium. Mm-hmm. But so far so good. We have in the one case that we measured it, just the two measures were so coincident with 2 seconds apart. It's nothing.
Yeah, and what's exciting about this, I think what a lot of people forget about this is that it's not that light is special. It's that the speed at which light travels is special, and that's the speed limit. It's just we're most comfortable and our most accessible kind of messenger at that speed is light. But all of the fastest things traveling in the universe are traveling at that speed. It's not just special that it's light. It's like gravitational information, photon information, potentially neutrino information. All of these things are just like capped at that limit. It's not that it's like, oh, light is special. It's just going as fast as it can on the Autobahn. And there's lots of other things going as fast as they can on the Autobahn too. So, or seemingly so. All right, moving to the next question. What two NASA missions have had their lifetimes extended beyond their planned completion dates in 2020? So two NASA missions, because they're NASA missions, well, I'm not going to reveal too much. People will probably Google this answer, but I can tell you that it revolves around two solar system objects. One is Mars and one is Jupiter. What do you guys think? Any ideas? Whoa, whoa, whoa. All the answers are coming in. Hubble, Juno, TESS, Opportunity, Insight, good ideas. All of them good ideas. Hubble, we're going to hold on to Hubble for as long as we can.
Hubble better not die.
That's right. Yeah,
Don't.
Hubble's launch date, Hubble's been operating since 1990. It's pretty crazy.
It is. I mean, look, it is because it is serviceable.
Yeah, indeed.
Right? It would have been vastly less useful if we hadn't been able to correct the optics and upgrade the instruments.
Indeed. Yeah. Oh, yeah.
JW is way scarier.
Hubble would have been dead on arrival had we not been able.
Well, you can compute, like you can go back and design algorithms to correct for the optical design flaw. Basically, right. There was like, you know, a difference between spherical and parabolic lenses. But no, we're glad that we were able to service that and yeah, nip that in the bud.
So lots of answers here. It seems like the overwhelming answer that people are posing is Juno. There's a lot with insight and opportunity, even some Voyagers in there. So the correct answers, one is in fact Juno. Juno is a mission that's been hanging out for the last 5 years around Jupiter, making some incredible images of Jupiter. I mean, it's not just there to make beautiful images, but by God, has it done that successfully. The fluid dynamics of the surface of Jupiter, the surface of Jupiter are just mind-blowing. But it's been measuring the magnetic field distribution on around the orbit of Jupiter, as well as surface composition, hydrodynamic studies, a variety of different things associated with Jupiter. And now that it's been extended till 2025, it's now going to pass by several of the moons of Jupiter. So it's going to make a close pass with Ganymede. It's going to make a close pass with Europa, being able to study some of the subsurface ocean on Europa. And then
find some aliens.
Perhaps,
find some aliens.
Perhaps find some
aliens
on Europa. and pass by Io a couple of times, the super volcanic moon of Jupiter. So it's super exciting, and I'm really happy that it has been extended. The other mission is InSight, this Mars mission that has been sitting on the surface of Mars for a couple of years. So this mission this illustration, which is not a real photograph. We didn't have a photographer up there taking a picture on the surface of Mars of InSight. The main thing that it's doing is it's studying the magnetic field of Mars. It's studying that thing off to the lower right is like a heat probe where it sticks this probe down into the surface of Mars to see the temperature profile and how it changes over time in the interior, down like maybe 5 feet, 6 feet. And then there's a really sensitive seismometer. So it's measuring Mars quakes and how frequent they are, what the distribution is, and what that tells us about the interior makeup of Mars. And that's really the key thing that it's being extended for is the seismometer. So either way, super exciting. And yeah, thank you NASA for extending these missions. When you spend like tons of money launching, it's not that much more money to keep it running for a few more years just to make sure that you can do relevant science for a bit longer.
Yeah, isn't it usually like some ungodly fraction of the costs go into just getting it up there?
Oh, yeah.
And safely landing?
Producing these
like
things.
95% or something.
Into the thing. Oh, a question relevant to Rachel's talk. What type of galaxy? Whoa, boom. What type of galaxy is our own Milky Way? People seem pretty unanimous in the decision.
Pretty emphatic about that one.
Oh, interesting.
Yeah.
Okay.
Yeah.
Wide spiral. All right. Mixing it up a little bit. Okay. So I included in the answers here. Oh, indeed.
Oh.
Or
I would say very lucky.
Galaxy. In the answers, I included the tuning fork diagram, so we could talk a little bit about the tuning fork. All right. So there's general consensus and a few different ideas here. the answer that I've provided, although Rachel may want to modify in some capacity, she's the observational galaxy expert here. Spiral or barred spiral, and I include a couple of these formal categories, and an image of what the Milky Way looks like, at least from one perspective, seemingly in some tropical climate with
Very nice looking perspective. Sign me up. It's pretty cold in Pittsburgh right now.
But yeah, so there's this classification scheme that we now know is a bit outdated in terms of how it was produced. But Edwin Hubble originally proposed it as a way of kind of classifying different types of galaxies. And we believe that the Milky Way sits somewhere between either a non-barred spiral or a barred spiral. Do you want to add anything to this discussion?
Yeah, I mean, the tuning fork is basically backwards. I mean, as is the case with a lot of astronomical nomenclatures, we named things based on some kind of old study like this. So things that live on the left side of this are called early type galaxies, and things that live on the right hand side of that are called late type galaxies. But like actually the evolutionary sequence, you probably got a hint of this actually from my talk, is actually goes in the other direction. And since, you know, in English at least, we read things from left to right. Often I'll show this in talks, but you know, like flipped. Because that's actually it's suggestive of being an evolutionary sequence, and actually Edwin Hubble thought that it was an evolutionary sequence left to right, but it's in fact the opposite.
Edwin, you were wrong. You were wrong, Edwin.
But, I mean, it's cool. They were still arguing about whether the universe was the Milky Way or not. So
yeah, just the fact that we know that the Milky Way is a galaxy, yeah, it's quite a thing.
It's cool. Like I'm happy to have a job and keep figuring these things out. I'm not complaining.
Indeed. All right, cool. Thank you guys. Thank you. Next question. What was the name of the rocket that launched the first person into space? This is exciting. So I guess we can ask people, who was the first person into space? Yes, Rocket 1. If it were done by SpaceX, that would be the answer. Whoa. Rocket 1, Sputnik, Saturn V, Vostok 1, Vostok, Sputnik. Okay. Got some students of history. Sputnik. Excellent. What do you guys think? And it's okay to be wrong. It's okay to be right. No one will burn up your tenure application if you're wrong here.
I mean, that's good.
I voted Sputnik.
Yeah, but I'm not confident in that.
No.
So Sputnik means satellite in Russian, and Sputnik was the first satellite that went to Russia, but it didn't have a person on it. It was just a little sphere that had a couple of pointy parts hanging off of it. And it was good at being a repeater of pulses to make sure that it was in a stable orbit. But Sputnik, despite the overwhelming response, is not the correct answer. It looks like the second most prominent answer of Vostok is indeed the answer. Or as the Cyrillic alphabet would have you read it, Bakhtok 1, Vostok was the first person in space was Yuri Gagarin. We're coming up on Yuri's night in the next couple of months. So Yuri Gagarin was the first person in space. He was part of the Soviet Space Agency. Happened in April. I forget the date. Someone I'm sure in the chat will one-ups me on that. April, and Vostok 1 went up, and it's this kind of crazy looking spaceship with big thrusters at the rear end. Vostok means east because the Soviets were really big on making this about the east and, the Soviet state. And because everything during that period was driven by nationalism, whether it was by the US or by the Soviet Union. But yeah, that's the answer. So that's all I got. Next question is, recently scientists proposed that what objects may actually be the mouths of traversable wormholes? Wormholes being things that you can travel through space-time very quickly. Excuse me. Space-time very quickly, like you see in a lot of science fiction movies, a lot of let's see, science fiction books. Interstellar featured this. What other major science fiction has featured? Yeah, Stargate, I think, has featured this. That's good. Stargate. Ooh, a block.
Stargates were the stargates, not the black holes.
Oh, were they not? I don't know. I like block hole. That's like the drink black hole. Cameron's coffee cup. But I don't even drink coffee. But I do drink this fine fundamental observation.
Why are you advertising for this beer?
Because now I'm intoxicated because I didn't realize it was 15% alcohol, and I just
you said that it was an imperial port or whatever.
Oh, I didn't realize it was that high. Black holes, singularities, AGNs, Twitter. That's not a bad idea. Okay, so the answer, this is really interesting paper that was written a few months ago, are in some ways everyone except the person who wrote Cameron's black hole and Twitter are correct. AGN, active galactic nuclei, which are supermassive black holes in the interiors of galaxies. Essentially what they proposed is that AGN are these conduits. They're the mouths of wormholes, as you can see in this diagram. And stuff flows in, but it also flows out of the AGN. And we do know that AGN, active galactic nuclei, are producing huge amounts of high energy radiation. But this essentially suggests that we should be able to, it gives a test for this. And it says that the energy that we see coming out of AGN, if it indeed is the mouth of a wormhole, you'd have super energetic collisions occurring in the wormhole between these like streams of material coming in one side and streams of material coming in the other side. And it would be so energetic that it would produce a much more energetic photon out the mouth than you would expect just from the accretion disk flow and what that would produce. And so you'd see much higher energy gamma rays coming out of AGN that could be normally explained by just normal accretion flow inflow into the black hole itself. So it seems kind of far-fetched, but on the other hand, they're producing a very clear observational indicator on whether or not their theory is true, which I certainly appreciate, instead of it just being like hand wavy, oh yeah, we have a really good idea, but there's no observational test. And this is saying like,
you mean like string theory?
Yeah, I wasn't so this is actually saying like, if you look at the AGN with a gamma ray telescope and observe gamma rays that are above this energy level, then it's indicative that it isn't just accretion flow physics, because you can't have accretion flows being as energetic as you would expect them to be. There has to be something additional, and that something additional is the collision of these like monolinear flows inside a wormhole, and then they spit out the like belch of these enormous collisions, these super energetic collisions. So I thought it was kind of cool, and it got covered. I wasn't just like scouring the archive for this result. This was covered in some popular media, but the paper is Pietrovich et al. 2020. It's kind of interesting. All right, moving on. How far away is the furthest known galaxy? This is a multiple choice because obviously there are a lot of distances at which the furthest known galaxy can be. Oftentimes astronomers refer to things in terms of redshift, which is kind of a proxy for distance to things. It's the velocity at which it's redshifted away from us, which tells us something about when how far away it is because of the expansion of the universe. But here I'm just giving actual distances. Like these are proper distances. And we've got some interesting things. So these light year, keep in mind that the light year values, the age of our universe is roughly 14 billion years. And so you might expect, not to pre-spoil things, you might expect that the distance to things would be on the order of that in light years, because it's taken that long for objects at that distance to travel their light to travel the distance to us. But we've got some interesting results, and this is a question that I think Rachel should really hammer down.
Yeah.
So
the answer is actually the least popular vote.
Indeed.
And the problem is that distance in an expanding universe is actually not the most, it's not as well defined as it is in our, normal everyday experience, right? And that's, partially because, so that the numbers that people were primarily choosing were what we would call light travel distances, basically. So that is the distance that photons that left the galaxy, whatever it was, 12 billion years ago, and traveled toward us. The problem is that that galaxy is embedded in an expanding space-time. And in the intervening majority of the history of the universe has expanded dramatically, such that instead of being 12 billion years, light years away, that space is now ballooned, and it's more like 400 billion years, billion light years away. And, there are actually lots of complicated different types of distances. In fact, when you think about distances that are so large that things are expanding with, we call it with the Hubble flow, with the expansion of the universe, then you have to be really careful about defining what you mean by distance. So what is traveling that distance? Is it a photon that's traveling that distance? Are you measuring a spatial scale at some different distance? And all of those things change because of the weird properties of an expanding universe. Super cool, super, full of mind-bending, tongue-twisting types of questions.
The way I like to think of it is that, so in a static universe where there's no expansion, we would expect that distant galaxy, it would be because the universe is only, on the order of 14 billion years old, it would only be 14 billion light years away. But as you just described, it's much farther away. The way I like to think of it is, think of that galaxy sitting on, when you go to the airport and there are those people movers. They're like flat escalators. They just move you along. The lazy people who don't
call those moving walkways, but okay, people movers, sure.
Whatever. So I like to think that galaxy got on the people mover, the moving walkway, going that way, and they sat on that thing, and then they threw a football to you, let's say 50 meters away, 50 yards away, and you caught it. But by the time you caught it, that football being the photons, by the time you caught it, they continued to move in the other direction as the universe expanded until you caught it and you were like, oh, well, when they sent it, they were only 14 billion light years away. But now they're like way 400 billion light years away because that people mover, that moving walkway, was way fast and it kept moving as those photons traveled to me.
Okay, but here's the bad thing. If you want to go shoot your signal back at that galaxy, you're hosed.
Oh, yeah.
Because it's completely causally disconnected from us.
Yes.
You can send whatever you want towards that galaxy and it'll never make it.
It's gone. It's gone.
So
And
we're
that's the
grasping
thing
at the
about-
last pieces of information from that corner of the universe.
Yeah, and that's the whole thing about like the future universe, because the expansion will continue and is accelerating. We will end up in a universe that's like totally causally disconnected from all the other parts of the universe. So we'll just be in like this little corner where we're like, oh, hey, stars in the Milky Way.
No, we're going to be in the Milkdromeda,
Oh,
and
milk.
we're going to be like, hey, stars. You're everywhere.
Yeah, but it'll just be our stars instead of the whole universe of stars. It'll just be the Milkomeda stars.
You know, there's nothing wrong with Milkdromeda stars. Actually, I think, you know, like there will still be things outside of the local group that won't
but
be
I'm talking
disconnected,
like
right?
the long term.
Yeah, I mean, I'll be out of a job.
Well, no, I'm
Right?
talking like 100
like-
times from now. I'm talking like 1,000 billion years from now.
Yeah,
A
I'm not
trillion.
going to live that long, I think.
Yeah, no,
I think.
not if we drink beer at this rate, certainly.
My hair's already ahead of me. It's fine.
All right. Moving on to the next question. Let's see what we got here. Okay. What is the smallest constellation in the sky? There's lots of constellations. How many? I think 60, 66, 88. There's something. 80. I forget. I'm sure someone will Google it and tell me. There
What
are a
does
lot of
smallest mean here? Like with fewer stars, or the spatial?
Smallest
is the
spatial, like
smallest?
angular area.
Yes, that's right. Ooh, Wendy's.
Just like, you know, astronomers don't actually mean the asterism, right? We don't mean the shape that's traced out by connecting the dots.
Yeah, that's right. The area covered. Ooh, dunno. Yes, someone being honest. Good work. Pleiades, unfortunately, is not, in fact, a constellation unto itself, not in the Western constellation system, certainly. The Dolphin one, I like that answer. Someone also...
That's because it's like correct. That's my favorite part.
Don't care. Okay, legit. Respect. Yep. A few different spellings of Pleiades, because Pleiades is like the hardest word to ever spell. I always have to look it up. I'm like, there's 4 vowels. What order?
Yeah, that should definitely never be on Wheel of Fortune.
Yeah, that's right. Ursa Minor. All right. Do you guys know? It's okay if you didn't.
I thought it's Dolphinus, right?
It's Crux.
Oh, really?
Yeah.
Hmm.
So the Southern Cross, which you can see here as the 4 brightest stars, making up, well, I guess any 4 stars basically make some sort of rhombus. In this case, they make a diamond, kind of a kite shape. They make a cross. The Southern Cross, you can see it on like several flags of the Southern Hemisphere, Australia, New Zealand. I'm sure there are others. A pretty identifiable set of 4 stars in the sky over the Milky Way. And what's interesting, so in the northern hemisphere, obviously many of you are familiar with the Big Dipper. The Big Dipper has 2 stars that point towards the North Star, so we can figure out what direction is north. You can similarly use the Southern Cross to figure out where the southern celestial pole is. It doesn't align with a star in the same way that we have a North Star, at least in present time. We won't always have a North Star. We didn't always have a North Star. It's not because that North Star is going to die or anything like that. It's just because the slow rotation of the northern celestial pole doesn't always align with a star. We're just coincidental that in present days it does, but 1,000 years ago it didn't, and in 1,000 years it won't. But anyway, that's a side note. In the southern hemisphere, you can use this kind of pointing model to be able to identify roughly where the actual southern pole is, and use that for like how do I find my way home? Okay, that direction is south. So what direction is east and west and so on and so forth.
Yeah, that's like Australia 101. As soon as you move there, the first part you go, especially if there are two international astronomers, that's the very first thing that will challenge you about, hey, where is the South Pole? You're like, no, I'm just drinking my beer. No, look, if you align this and that, you can then find like, cool, okay, cool. Now I have a story to tell and a lot of tattoos to recognize. Apparently they're very popular because Southern Cross is in the heart of so many people.
So many people. They've got to represent. Yeah. I don't see a lot of
get
people.
the Magellanic Clouds.
Oh, yeah. Right.
Just amorphous blobs.
So there was already a discussion of the Magellanic Clouds at the end of Rachel's talk. But yeah, the Magellanic Clouds are these two dwarf galaxies that are orbiting the Milky Way. You can see them here on this diagram as well. They have
a scale.
Yeah, that's right. They have about the same surface brightness as the Milky Way. So if you're in a dark enough site to be able to see the Milky Way in the southern hemisphere, you could probably see the Magellanic Clouds if they're up at that particular time, which they probably should be because they're close to the southern celestial pole.
They are awesome.
Yeah, they're super cool. It's cool to see. And the only reason they're called the Magellanic Clouds is because Magellan, the explorer, the Portuguese explorer, was the first Westerner to go to the southern hemisphere. And like, I guess he didn't come back alive, but his crew came back.
Claimed them.
Claimed them, but it should really be named, I don't know, it shouldn't be named after some Portuguese explorer, some conquistador, but it is, unfortunately. So,
however, you should get ye to the southern hemisphere in a dark spot because it's really incredible.
Yeah, they're cool.
And if you don't believe that galaxies eat other galaxies, you can't ignore it when you see the Milky Way and the other two galaxies nearby.
It's going to take a big chomp and it's going to eat them.
Yeah. It's going to assimilate.
It's going to assimilate like the Borg.
All of your stars belong to
us. That's right. Okay. We always have a Star Wars question because I'm a silly Star Wars fan. And what planet was the Imperial Center? And it was a planet-wide city. What do people think is the answer to this fine Star Wars question? I know a lot of people give me a hard time and they're like, Star Trek is better than Star Wars. And I say, lay off. I really like Star Wars. Oh, look at Rocket.
And I say, Battlestar Galactica.
I love that Portlandia about Battlestar Galactica. Let's just watch another episode. Just another one. Ooh, who cares? We're getting a lot of spicy audience tonight. I don't care. I don't care about the smallest constellation, and I don't care about Star Wars.
I think they're drinking with us.
Yeah, maybe. Trantor.
What's a Star War?
What's a Star War? That's a good question. I don't know. Who cares? Trantor, Coruscant, Rocket Raccoon. What Star Wars? New York City, Galactica. Okay, Galactica. Isn't Galactica a semi-analytic model? No, that's Galacticus by Andrew Benson. That's a good code. What's new? Alderaan. Okay. Spock. Nice. Okay, I'll just get past this. The most popular vote indeed, Coruscant. Coruscant, the capital of the Empire and later the Republic, or prior to that, the Republic. I didn't know it had like signs on the surface here, but yeah, it's featured in which episode? Episode 1, episode 2? I think both.
I don't know because I won't rewatch those.
Yeah,
sorry.
I haven't watched them in a long time. They kind of burned my retina. But
yeah, it's Jar Jar Binks.
Yeah, Jar Jar.
Yeah.
Anyway,
no.
Citywide planet. There's always a planet Star Wars question. I kind of stick to that. And yeah. Oh, speaking of Star Wars, my sister got me these sweet socks. I know nobody cares, but I'm going to show them anywhere because they have Baby Yoda Baby. Oh wait.
Oh, that's pretty awesome. Don't fall over. Don't fall over.
I know. Baby Yoda's on the front. Pretty sweet.
Was that for Christmas?
Yeah, Christmas gift. Who is the first astronomer to use a telescope? Lots of astronomers.
And other people used telescopes before this person.
Rachel Bezanson, perhaps, is the first astronomer. Perhaps Igor Andreoni, perhaps.
Italians speak out. That's your time.
Was.
Show the world we did something good other than pasta.
Pasta.
Yeah, pasta would be alone enough.
Alone enough. Copernicus. Okay. Copernicus is up there. What, Edwin Hubble doesn't sound Italian enough to you people? God.
We can try to Italianize the name.
We could just do it in an italic font. That's not the same thing, right?
What about like
Edwino Abbone. Abbone. I don't know. I'm at the third beer. I can't even do that.
what was the Bodie McBoatface? Maybe there's Telescopy McTelescopy or something like that.
Yeah, that's why humans don't get to name things anymore.
Ptolemy's
Bodie McBoatface.
Bodie McBoatface. All right. The people have spoken. The answer.
People are right.
The answer is indeed Galileo. Galileo Galilei. All right. I chose this because we have an Italian as one of our people here. Can you tell me? It's pretty awesome if your name is also your last name. Why aren't you Igor Igori? Or why aren't you Rachel Richelli?
Well, actually, that
because I'm not Italian.
But my name is Russian for weird reasons, even if I'm 100% Italian. But a very common name in Italy for male is Andrea. So I could be very, very easily Andrea Andreoni. And I'm really sure someone exists in the world with that name.
So why is this possible? So does his last name mean like son of Galileo? Is he like Galileo, son of Galileo?
Probably, yeah.
Okay.
Yeah, if from Latin, that could actually make sense.
Cameron McCameron or something like that. I could do that in
Hummel McHummels.
Hummel McHummels. Yes, the answer is indeed Galileo. He was a super badass. He was the first person to use a telescope looking up at the heavens. He was not the inventor of the telescope. The inventor of the telescope was a Dutch optics maker named Hans Lippershey, who designed the telescope. But Galileo was one of the first people who actually utilized it, and certainly the first person who utilized it by looking up at the heavens and looking. He made significant observations of sunspots on the surface of the sun, probably damaging his eyes, as well as the Galilean moons, which are the moons that orbit around the four major moons which orbit around Jupiter, as well as the surface of the moon and identifying dark spots, which he thought were seas or oceans, and calling them maria, which is the Italian word for seas. Which they are not, in fact, seas. But yeah, he made a lot of contributions. Okay, that's the end of our presentation.
Dude, have you seen the images of sunspots from the new telescope, the Inouye Solar Telescope?
No. Tell me more.
Dude, they're so cool. just look them up. Like, brand new solar telescope.
Brand new solar telescope.
Yeah, I mean, I know this because I'm a Aura member rep. Yeah, let me see if I can find it.
Are you repping the brand here? What is this?
For a solar telescope?
Well, you can buy solar telescopes. Oh,
no. It's like it's here.
Share your screen.
Yeah. I'm trying to.
I'm seeing super high res images of the spicules on the surface of the sun.
Yeah. So like the size of Texas. So previous images were like way less high resolution. So you can see all of these convective zones on the surface of the sun. Let's see that this actually plays. It is super cool.
That is super cool.
Anyway, for questions for next time.
That's right.
You know.
Yeah. So let's see. I haven't been monitoring the audience questions throughout this because I've been too busy doing stuff. Any questions for us? I've been yapping away for the last 30 minutes about bullshit.
There's a lot of people yapping about Galileo too, so
Yeah,
it's okay.
That's what I was yapping about. You guys have any pet projects you want to advertise for the next 5 minutes? It's okay.
Pet projects. I could talk about JWST.
Yeah, talk about JWST. Hopefully it'll launch. We'll see.
Yeah, Halloween this year. I'm saying it. This year is 2021, and it is supposed to launch this year. We say this with enthusiasm because the date keeps getting shifted, including getting. Oh, the original date? I don't know what the original date was. It was a long time ago.
Like a decade.
But anyway, so James Webb Space Telescope is it's often referred to as the successor to the Hubble Space Telescope, but in many ways it's very different. So it is equipped with a number of instruments that are all kind of focusing on the longer wavelength radiation. So the basically the red end of the optical out into the infrared, and not just the near infrared, which the Hubble Space Telescope is sensitive to, but really out into the near and the mid infrared. And that's super useful for a number. So first of all, the reason that we have to put that kind of instrumentation on the James Webb out in space is because the Earth's atmosphere has a couple of windows where it transmits near infrared light, but the vast majority of light at those wavelengths is opaque. It is opaque to that light, so it doesn't transmit. So you really need to get above the Earth's atmosphere. And it's really exciting because either cool things that emit much of their light at the longer wavelengths, like say planets or low mass stars,
galaxies,
and super distant objects that emit most of their light probably in the optical, but are so far away that the stretching of the universe has cosmologically redshifted their photons out into the infrared. The James Webb Space Telescope will blow away the previous most distant object record. It will find galaxies as soon as they formed. So the current record holder that we talked about, it's ridiculous that thing exists. It formed, 300 million years after the Big Bang. A huge galaxy already existed. We will know when galaxies started to exist and started to turn on, because the James Webb Space Telescope will find them. And obviously that's what I've thought about the most with JWST, but it's super exciting. We hope it unfurls. If it doesn't unfurl properly, there's like this sunshade. And I can't remember exactly, so it opens up to shade different parts of the instrument from the sun because it has out in space. And I think it has to be precisely unfurled to the centimeter, otherwise it fries the whole thing.
What? Really? It's that precision? Don't fry the whole thing. It's like $4 billion, and it's taken 20 years to develop. They can't miss a millimeter.
And we can't service it.
Oh yeah, I know.
Because it's not, so the Hubble Space Telescope orbits the Earth, which has its pros and cons. It's serviceable, it's close, it's easy. But the downside is that, it spends a significant amount of time behind the Earth. I will take that because James Webb will be way too far away and we'll never be able to search it.
Because once you go to L2, you're screwed. You can never touch it again. So if you messed up, it's done. It's gone.
But I choose to be optimistic about it this time because it's the only option. Trust me, Obi-Wan.
The only option.
You're my only hope.
Boy. Indeed. Oh wow, we got a couple of questions in this time.
There are a lot of single points of failure. You also want to keep the instruments cool, right? That's part of why you want to shade it.
It's true. You do.
I also hope that JWST performs flawlessly for much longer than it was planned, much like the Hubble Space Telescope, but there are actual fundamental limitations.
What's its official time?
5 years.
Oh, really? What was Hubble's original? Like
I don't know. I think it was like 10 or something, but it's
lasted
way.
Yeah, I think 10 too.
Yeah.
Good job, Hubble. You guys rule. Way to go.
Hubble is definitely the little engine that could.
Yeah.
It is the workhorse. Our field would be just fundamentally different. Yeah, I think there are very few branches of astronomy that have been uninfluenced by HST.
That's right.
Certainly the three of us.
Yeah, certainly. Yeah, I wouldn't be employed. I have several HST grants that have
yeah.
So, quick announcement for our audience. We will probably have some shorts because not everybody on YouTube wants to watch a 2-hour-long stream about people drinking beer and drunkenly talking about astronomy. You're not like clicking through and you're like, oh, maybe I'll watch that 2-hour thing. That sounds pretty good. No. So we're going to have some shorts where it's like a 10-minute explanation of something. I haven't figured out what something we're going to explain. Several somethings. And then at our next public lecture, I'm going to try and do live observing with the telescope from here in Pasadena on my balcony. So it won't be great.
Are you going to see like Jupiter?
Oh yeah, that's right. Well, Jupiter will already have set. I'll see Mars. I will see Mars. I will see the Pleiades. Thank you very much. I will see the Orion Nebula, and I will see the moon. Probably will be my.
I mean, I know that like I'm contractually not allowed to say this, but like it's kind of a bummer that Jupiter and Saturn are so close together, because if you lose one, you lose the other, and like they're actually the coolest things to observe with a small telescope.
We'll be able to see them come again in the summer.
I know.
But anyway, for our audience, you'll be able to see how you actually can see stuff with the telescope, what you can actually expect to see from looking in super crummy skies in Los Angeles with a telescope, and other stuff like that. So stay tuned. It'll be great. I can't promise there probably won't be alcohol involved, but there might. Probably won't be this, since I just figured out that it was 15% alcohol, which is just outrageous.
Did you finish it?
Of course I finished it. I was listening
Cameron,
to
I'm not even sure that that's called a beer. Isn't that like not actually allowed to be called
That's
more
than a wine. Like strong wines are 14 degrees or so.
It wasn't distilled. I believe it was
yeah, but there are limits to, like, I don't know, maybe you don't have any rules in California, but like
this isn't Utah. We don't have a 3.5% ABV limit.
The Germans would not call that beer.
Oh, they would call it manna from heaven is what they would call it, because it was wonderful. It was very good.
Yeah, you call it beer for convenience, just to have the extra hit for free.
Anyway, thank you to our audience for sticking around for 2 hours of our ramblings. Thank you for Rachel. Wonderful, wonderful presentation. Thank you, Igor. Wonderful presentation. You guys were great, and you kept this alive despite my nonsensical bullshit. And thanks for everybody with the quiz. I know it wasn't the best quiz, but there were some pretty decent discussion topics. So our next event is next Friday, public lecture, from whom I don't yet know, but it'll be good, I promise. And I'm going to make sure that I smuggle out a telescope so that we can actually, I'm not allowed to go back to the astronomy department because of the pandemic, but I'm going to sneak in and steal a telescope so that we can do some viewing. Don't tell Caltech that I'm going to steal that telescope though.
You know, it says powered by Zoom in the lower right-hand corner.
I know, powered by Zoom, Caltech. Don't tell Caltech that I'm going to steal a telescope for this event. All right. Have a great evening. Don't start any insurrections, and keep observing the sky. All right. I think that's all I got. All right.